Welcome to part 3, Maps between Manifolds. Now that we know what a smooth manifold is, the natural next question is, what are the right maps between them? In this part we will build the entire theory. Smooth maps, rank, immersions, submersions, and the major structural theorems that organize it all. Part 2, build the definition of a smooth n-manifold from the ground up. Hausdorff, second countable, locally Euclidean, with a maximal C-infinity atlas. We verified this on Rn, open subsets, the sphere Sn via its stereographic atlas, and the torus T2, and proved the partition of unity theorem, which is the main tool for patching local constructions into global ones. Part 3 asks what the correct maps between manifolds are. We will define smooth maps and diffeomorphisms, introduce the rank and the hierarchy of immersions, local diffeomorphisms, and submersions, define critical and regular values, prove the 4 structural theorems: Sard, the theorem of the rank, the inverse map theorem, and the implicit map theorem, and characterize quotient manifolds. There are 3 requirements a reasonable definition of smooth map must satisfy. First, it must agree with the classical notion when M and N are open subsets of Euclidean space. Second, it must be intrinsic, independent of the choice of charts. Third, it must be local. Smoothness at P depends only on the behavior of the map near P, not on the entire map. The strategy borrows coordinates from both sides. Fix a chart phi around P in M and a chart psi around phi of P in N. Form the composition psi composed with phi inverse. This is a map between open subsets of Euclidean space where C infinity is already defined. Requiring that composition to be C infinity is the definition. There is one thing to check before we can call this a definition. Does the answer change if we swap to different charts? Fortunately, no. And the reason is exactly the same one we saw in part 2 when we verified that smooth functions are chart independent. The C infinity compatibility of the atlases, combined with the chain rule, guarantees that if the local representative is C infinity in one chart pair, it is C infinity in every pair. Time to make the sandwich construction concrete with a picture. We have 2 manifolds, M on the left in yellow and N on the right in green. Below each manifold sits its Euclidean shadow, Rm below M and Rn below N. Step 1. The chart map phi pushes the point P down into Rm, flattening the curved manifold into coordinates. Meanwhile, the map phi itself carries P across to phi of P inside N. This is the map we are trying to understand. Step 3. The chart map psi then flattens phi of P down into Rn, giving us coordinates on the target side as well. The red arrow at the bottom is the key object. Psi composed with phi inverse. This is the local representative, a completely ordinary map between open subsets of Euclidean space. Requiring it to be C infinity is what it means for phi to be a smooth map between manifolds. Now that we have the geometric intuition, here is the formal definition capturing exactly that sandwich picture. The map phi from M to N is smooth if for every chart U with phi on M and V with psi on N, the composition psi composed with phi inverse, mapping from the phi image of the overlap of U and the pre-image of V into psi of V, is C infinity as a classical map between open Euclidean sets. We give this sandwich composition a name, the local representative of phi, also called phi in local coordinates. It is an important tool in most computations in differential geometry. And crucially, as we promised, this definition does not depend on the choice of charts. Any 2 local representatives of the same map are related by pre- and post-composition with the C infinity transition maps of the atlases. So, if one local representative is C infinity, they all are. Among all smooth maps, the most restrictive condition is invertibility with a smooth inverse. A diffeomorphism from M to N is a bijective C infinity map whose inverse is also C infinity. When such a map exists, M and N are diffeomorphic, indistinguishable from the point of view of smooth calculus. You might wonder, if a map is bijective and smooth, is its inverse automatically smooth? No. And this is a subtlety that distinguishes smooth geometry from topology. The standard example is x cubed on the real line. This is bijective and perfectly C infinity in both directions of the domain. But its inverse, y to the power of 1/3, has a vertical tangent at the origin and fails to be differentiable there, so it is not a diffeomorphism. Smoothness of the inverse is therefore an independent condition. Diffeomorphic manifolds are completely interchangeable from the point of view of smooth calculus. Every smooth function, vector field, or tensor transfers canonically across the diffeomorphism. Diffeomorphism is the correct notion of isomorphism in the category of smooth manifolds, just as homeomorphism is the correct notion in topology. Here is the x cubed example drawn side by side with its inverse. On the left, phi of x equals x cubed. An S-curve, C infinity everywhere, bijective. On the right, the inverse. The graph looks smooth everywhere except right at the origin, where both branches arrive with infinite slope, forming a sharp cusp. A function with a vertical tangent is not differentiable. This is the failure point. This single bad point at the origin disqualifies x cubed from being a diffeomorphism of R. The moral, bijective plus C infinity is not enough. We need smoothness of the inverse as an explicit, independent condition. With the definition established, here are the main examples. The most basic, any smooth function f from M to R is a smooth map from M to the one-dimensional manifold R. Going the other way, a C infinity parametrized curve gamma from the open interval AB into M is a smooth map from the one manifold AB. If S is a smooth submanifold sitting inside M, the inclusion map of S into M is automatically smooth. Submanifolds come with this for free. The canonical projection from a product M cross N to M, dropping the second factor, is smooth. And one of the most important examples in the whole course, if G is a Lie group, the group multiplication, a map from G cross G to G, is required to be smooth. We will talk about Lie groups later on. The examples we just saw treat smooth maps as global objects, functions defined on entire manifolds. But to understand what phi does at a single point P, we need something more refined, a linear approximation, just as the Jacobian matrix is the linear approximation of a map between Euclidean spaces. On manifolds, there are no canonical coordinates, so we cannot write down a Jacobian directly. We need a vector space attached to M at each point P, a space of infinitesimal directions at P. On Rn, a tangent direction at P is encoded by a straight line through P with velocity v at time 0. On a manifold, straight lines make no intrinsic sense, but smooth curves do. Any smooth curve gamma through P, meaning gamma of 0 equals P, has a well-defined velocity in any chart. The vector phi composed with gamma prime of 0 is in Rn. Different curves with the same chart velocity represent the same infinitesimal direction on M. Collecting all curve velocities at P gives the tangent space Tm at P, an n-dimensional real vector space attached intrinsically to M at P. The differential phi star P is the linear map from Tm at P to T phi Pn, encoding phi's infinitesimal behavior at P. Its rank as a linear map is the rank of phi at P. Every subsequent definition in part 3, immersion, submersion, critical point, is a statement about this single linear map. Here is the formal definition. Let M be a smooth n-manifold, P a point of M, and U and phi a chart around P. A smooth curve through P is a C infinity map gamma from a small open interval containing 0 into M, with gamma of 0 equal to P. We declare two such curves gamma and eta equivalent if the velocity vectors of phi I composed with gamma and phi composed with eta at time 0 are equal as vectors in Rn. The tangent space of M at P is the set of all equivalence classes of smooth curves through P under this relation. Does the equivalence relation depend on which chart we use to measure velocities? No. If psi is another chart around P, the transition map psi composed with phi inverse is a C infinity diffeomorphism. The chain rule then says phi composed with gamma and phi composed with eta have the same velocity at 0, if and only if psi composed with gamma and psi composed with eta do. The equivalence relation, and hence Tm at P itself, is completely chart independent. The vector space structure on tangent space at P is inherited from Rn via any chart. Map the equivalence class of gamma to its chart velocity phi composed with gamma prime of 0. This is a bijection onto Rn, and addition and scalar multiplication defined through it are chart independent by the same chain rule argument. So the tangent space at P is a n-dimensional real vector space. The definition is most transparent on S2. Here is the sphere in R3, and we fix the point P, the red dot. The tangent space of the sphere at P is the flat plane tangent to the sphere at P, shown in blue. Every tangent vector at P is a vector in this plane. Here are two smooth curves through P. The green curve is a circle of latitude. It moves along the sphere at constant height, sweeping around P. The yellow curve is a meridian. It arcs over the top of the sphere through P. Each is a C infinity map from an interval into S2 with value P at time 0. At P, each curve has a velocity vector. The green arrow is the velocity of the latitude circle pointing in the horizontal y direction. The yellow arrow is the velocity of the meridian, pointing diagonally downward along the sphere surface. Both arrows lie in the tangent plane. These two velocity vectors are two linearly independent tangent vectors, spanning the 2D tangent space. The tangent space of the sphere is two-dimensional, matching the dimension of the manifold, and sits inside the ambient R3 as a flat 2D plane through P. Every smooth curve through P contributes one element of TPS2, the equivalence class of its velocity. The full tangent space collects all of them. Given the definition of the tangent space, the differential follows directly. Let phi from m to n be C infinity and gamma a smooth curve through P. Then phi composed with gamma is a smooth curve through phi of P in n, and its equivalence class is a tangent vector in T phi Pn. The differential phi star P sends a tangent vector gamma in Tm at P to the tangent vector phi composed with gamma in T phi Pn. Push the curve forward through phi, then take its equivalence class at the image point. That is the entire definition. If gamma and eta represent the same tangent vector at P, the chain rule forces phi composed with gamma and phi composed with eta to have the same velocity at phi of P, so they represent the same element of T phi minus Pn. In local charts phi around P and psi around phi of P, the differential phi star P is the linear map given by the n by m Jacobian matrix of the local representative psi composed with phi inverse, evaluated at phi of P. This ties the abstract curve definition to concrete matrix computation. The rank of phi at P is the rank of the differential as a linear map. The rank is an invariant since a change of charts conjugates the Jacobian by invertible matrices on both sides. Every definition that follows in part 3, immersion, submersion, local diffeomorphism, critical point, is a statement about this linear map. Smoothness is a binary condition. A map either is or is not C infinity. The rank provides a finer quantitative invariant at each point. Fix a chart phi around P and a chart psi around phi of P with phi of U inside V. The local representative psi composed with phi inverse is a map from an open subset of Rm to Rn. The rank of phi at P is simply the rank of the Jacobian matrix of that local representative, evaluated at phi of P. This is a number between 0 and the minimum of m and n, measuring how many linearly independent directions the differential of phi sees at P. Just as with the definition of a smooth map, the rank does not depend on which charts we use. A change of charts conjugates the Jacobian matrix by invertible matrices on both sides, and conjugation by invertible matrices preserves rank. Three cases side by side at the level of tangent spaces, where rank is measured as a linear algebra condition. On the left side, we have an immersion. The source is two-dimensional, the target three-dimensional. The differential maps Tm at P injectively onto a subspace inside the larger target. The image does not fill the target, but no non-zero vector is sent to 0. In the center, we have the local diffeomorphism, equal dimensions, full rank. The differential is a square invertible matrix, an isomorphism of tangent spaces. Source and target are the same size, and the map between them is a perfect bijection. On the right side, we have a submersion. The source is three-dimensional, the target two-dimensional. The differential collapses the extra direction and maps surjectively onto all of T phi Pn. The image is the entire target tangent space. One more time, immersion goes with injective, submersion goes with surjective. Keep this in mind, it will be the organizing principle for everything that follows in this part. Now we promote these pointwise rank conditions to global conditions on the entire map. Let phi from m to n be C infinity. 1. We call phi an immersion if the differential phi star P is injective at every point, P. Equivalently, if the rank of phi is constantly m. Injectivity means no non-zero tangent vector is sent to 0. 2. We call the pair m with phi a submanifold of n if phi is a one-to-one immersion. That is, an immersion that is also injective as a set map, so its image does not self-intersect. 3. We call phi an embedding if it is a one-to-one immersion that is additionally a homeomorphism onto its image equipped with the subspace topology inherited from n. This condition rules out the self-intersecting pathology we will see in a moment. 4. We call phi a submersion if the differential phi star P is surjective at every point P, equivalently if the rank of phi is constantly equal to n everywhere. Surjectivity means the differential hits every direction in the target tangent space. The rank R is bounded by minimum of m and n. The three extremal cases, where R achieves the maximum possible in each direction, organize smooth maps into a natural hierarchy. First extreme, rank equals m. Second extreme, the dimensions are equal. Third extreme, rank equals n. Here is the figure 8 curve in the target plane R2. The parametric map traces this curve as t runs from negative pi to pi. The red dot traces the curve. It passes through the center only once. The map is injective. Now pay attention to the crossing point at the origin. 4 branches of the curve arrive from 4 distinct directions. The 4 green arrows mark the 4 distinct tangent directions at the origin. A small open ball around it in the image topology sees all 4 branches simultaneously. The image sees 4 branches at the crossing. In the domain, only a single arc passes through t equals 0, highlighted here. The two topologies disagree. The map is a one-to-one immersion, but the homeomorphism condition onto the image fails at the origin, so it is not an embedding. A one-to-one immersion need not be an embedding. The figure 8, which we just visualized, is the standard counterexample. It passes through the origin exactly once at t equals 0 and is injective everywhere. But as t approaches plus or minus pi, gamma of t approaches the origin from 2 additional directions. Any small neighborhood of the origin in the image meets 4 branches, while the pre-image in the domain is just a single arc around t equals 0. The subspace topology on the image and the domain topology disagree. An embedding is the stricter condition that rules out this pathology. When phi is an embedding, the image carries exactly the right topology. The smooth structure it inherits from n agrees with the one from m. Whitney's embedding theorem guarantees this is always achievable. Every smooth n-manifold embeds in R to n. Embedded submanifolds are the clean, well-behaved notion we use throughout the rest of the course. Having seen why embeddings are the right notion of submanifold, let us now collect the main examples, starting with immersions. The inclusion of Sn into Rn plus 1 has rank n everywhere. The sphere sits in Euclidean space with no self-intersection and no topology mismatch. Any parametrized curve with non-zero velocity is a rank 1 immersion. The non-zero velocity is exactly the injectivity of the differential at each point. Now a few examples of submersions. The product projection from M cross n to n. It drops the first factor and hits every direction in the target tangent space. The quotient map from Rn to Tn, wrapping the plane onto the torus, is a submersion because locally it is just a translation, which has full rank Jacobian. The rank can drop below its maximum at individual points. A point P in M is a critical point of phi if the rank at P is strictly less than n. That is, the differential phi star P is not surjective and fails to reach every direction in the tangent space of n at phi of P. The image of a critical point is a critical value. Any point of n that is not a critical value is a regular value. Any point outside the image of phi is always a regular value. There is no pre-image to check, so no critical points can be hiding there. This convention will matter when we state Sard's theorem. The most important special case of a critical point is when the target is just the real line. When n is R, the surjectivity condition for the differential simplifies dramatically. A point P is a critical point of a smooth function f precisely when the linear map f star P from Tpm to R is the zero map. There is no direction in Tpm that f can detect. In local coordinates, this simply says all partial derivatives of f vanish at P. This is exactly the familiar calculus condition for a critical point, and f of P is then a critical value. Here are critical points on 2 classical surfaces. On the left, the bowl f equals x squared plus y squared, a paraboloid opening upward. On the right, the saddle f equals x squared minus y squared. Both surfaces have the origin as their unique critical point, the one place where all partial derivatives vanish. The red dot at the origin of each surface marks the critical point. At every other point, the differential is surjective, and the point is regular. For any regular value c, the level set f inverse of c on the bowl is a smooth circle, a one-manifold as expected. This is a consequence of the implicit function theorem, which we will discuss later. Critical points are not all geometrically equivalent. At a critical point, the first-order information, the gradient, vanishes by definition. The second-order behavior is captured by the Hessian. The Hessian of f at a critical point P is the bilinear form hf at P, mapping a pair of tangent vectors to a real number. Given u and w in the tangent space at P and any vector field x extending u, meaning x evaluated at P is u, we set hf of u, w to be w applied to xf, evaluated at P. Here xf denotes the directional derivative of f along x. In local coordinates, the sum of xi times the partial of f with respect to xi. In local coordinates, the Hessian is simply the matrix of second partial derivatives of f at P. A critical point is called non-degenerate if this Hessian bilinear form is non-singular. Equivalently, the matrix of second partials has non-zero determinant at P. At a non-degenerate critical point, we define the index, the number of negative eigenvalues of the Hessian counted with multiplicity. The index measures how many independent downhill directions f has at P. Non-degenerate critical points cannot be destroyed by small perturbations of f, and they carry the most geometric information. The index makes the distinction between different types of critical points precise. The first example is the paraboloid, which has a minimum at the origin. Both Hessian eigenvalues are positive, so the surface curves upward in every direction. Index 0, no downhill directions at all. The red dot marks the unique critical point. The second example is the saddle surface, which has one eigenvalue positive and one negative. Curvature upward in one direction, downward in the other. Index 1, exactly one independent downhill direction. The third example is the inverted paraboloid, which has a maximum at the origin. Both eigenvalues are negative. The surface curves downward in every direction. Index 2, both independent directions are downhill. Before moving on, we should check that the Hessian is well defined, independent of the choice of extension x and independent of coordinates. This works only at critical points. In local coordinates, w applied to xf splits into a Hessian term involving second derivatives of f and an extension term involving first derivatives of f times how x varies. At a critical point, all first derivatives vanish. So the extension term is 0, and the Hessian depends only on u and w, not on the choice of x. Coordinate independence follows from the same expansion. Under a change of coordinates, the Hessian matrix transforms by congruence. H maps to A transpose HA for an invertible matrix A. Congruence preserves both non-singularity and the count of negative eigenvalues. To state Sard's theorem, our next major result, we need the notion of a set having measure 0 on a manifold. We will build this carefully, starting with the familiar Euclidean version. A subset S of Rn has measure 0 if, no matter how small we choose epsilon to be, we can cover S by a countable collection of open cubes whose total volume is less than epsilon. Intuitively, S is geometrically negligible. You can hide it inside arbitrarily thin coverings. We extend this to manifolds in the natural way. A subset S of M has measure 0 if we can cover S by charts such that in every chart, the coordinate image of the intersection of S with that chart has measure 0 in Rn. Does the answer depend on which charts we use? It does not. Suppose a second atlas covers S and each coordinate image also has measure 0. On any overlap, the transition map side J composed with phi I inverse is a C-infinity diffeomorphism. The change of variables formula bounds the Jacobian determinant of that transition map on compact sets, so the diffeomorphism sends measure 0 sets to measure 0 sets. The two atlases therefore agree on exactly which subsets of M have measure 0. Here is what measure 0 looks like on the unit interval. The set S is the sequence 1 over n, red dots at 1, 1/2, 1/3, and so on, clustering towards 0. Can we cover it with arbitrarily small total length? Yes. Cover the nth point by an open interval of width epsilon over 2 to the n. The green rectangles show these intervals. They shrink rapidly towards 0. The total length is epsilon times the sum of 1 over 2 to the n. A geometric series summing to 1. So the total length is just epsilon. Since epsilon can be chosen as small as we like, S has measure 0 despite being infinite. Before stating Sard's theorem, consider the extreme case, a constant map phi equal to Q0. Every point of M is a critical point. The differential is identically 0. The rank is 0. The critical set is all of M, yet the set of critical values is the single point Q0, which trivially has measure 0. That raises the natural question, is this always true? Even for complicated maps where the critical set is large, can the image of those critical points always be forced into a measure 0 set? The answer is yes. And this is Sard's theorem. No matter how large or complicated the critical set, its image has measure 0. The worst case points in the source are invisible from almost every point of view in the target. Here is the function f of x equals 1 minus e to the negative x squared. It has a unique minimum at the origin and rises toward 1 on both sides. The derivative is 2x times e to the negative x squared, 0 only at x equals 0. That is the unique critical point. Its image is f of 0 equals 0, a single point which trivially has measure 0. Every other output, every c strictly greater than 0, is a regular value. The green segment marks all of them. They fill almost the entire range. Sard's theorem says this is always the case for any C-infinity map. The critical values form a measure 0 set, and regular values are generic. Here is the formal statement of what our picture illustrated. Let phi from M to n be C-infinity. Then the set of critical values of phi has measure 0 in n. Equivalently, almost every point of n is a regular value, in the precise sense that the set of exceptions has measure 0. The geometric payoff is immediate. If the dimension of M is at least the dimension of n and q is a regular value of phi, then the entire preimage of Q is a closed submanifold of M of exactly the expected dimension, the dimension of M minus the dimension of N. Sard guarantees that such regular values exist abundantly. They fill an open, dense set. That completes part 3a. We have built the full language for maps between manifolds. Smooth maps are defined via C-infinity local representatives, and the rank of a map at a point organizes everything into three extremal cases: immersions, local diffeomorphisms, and submersions. We defined critical points as the places where the rank falls short of the target dimension, and we stated Sard's theorem. No matter how large the critical set, its image in the target has measure 0. Regular values are therefore the generic case, dense and abundant. In part 3b, we turn from the language of maps to their deep structural theorems. The theorem of the rank will show that every constant rank map is, in the right coordinates, just a linear projection. The inverse map theorem gives us local invertibility from a single non-zero determinant. The implicit map theorem turns equations into smooth manifolds. And the theorem of the closed graph will tell us exactly when a quotient construction succeeds. Bye.